Alright guys, I'll go ahead and get started. So if you look at the website, I just updated some of the dates. So the LCDs and sensors, let me display it there real quick. LCD sensors, the interrupt, that tutorial, it should be due today at 8 a.m., but I move it to Friday, so give you a little bit more time to work on it, which is homework 4, okay? And then there's a soldering, because we have the PCB board. I really want you guys to practice on soldering the surface mount components on the board. So I'm going to give you a credit if you do it. So it's homework 5. Okay, if you solder your power PCB board and report the results to the website, just put another homework 5 report, show the correct voltages, and then I'll give you credit on that. So if you don't have an adapter, you can request one from me. I have a lot, so you can directly plug in and then look at the voltages. And homework 6 is a really short tutorial from today. I'm gonna introduce that really quick. And so the oximeter PCB is on the way here. I think we're going to receive it probably, today is Wednesday, maybe Friday or Monday next week, possibly. So next week, expect another PCB soldering and testing homework assignment, maybe homework like 8, okay? And you'll work on that one, soldering that PCB, assemble it to your 3D printed parts, the container, and show the final product. So that's going to be homework 8. Since I really want you guys to finish that project. Okay, so I'm going to give you the credit for that, for doing that. Okay, and now let's get into the tutorial for today. So PID control is very useful. You know, there's a overshoot, then you feed the signal back to correct the input and eventually make it correct the value. Okay, so there's a lot of examples in real world which you can think about that you need a control in there, control system in there. It's just everywhere almost, right? Do you have any examples you can talk about? Yeah, airplane. Temperature sensor, just a sensor, right? Probably say thermostat. Yeah, thermostat at home, okay? And so we developed for the EPA project, I have the box in my office. So we have to heat up the PCR tubes on the top, so it's not getting the water condensed on the top of the lid. So we have to control at 100 Celsius temperature degree, and whenever it's overshooting, we have to cool it down. So we don't have a cooler for the top, so we just turn off the power supply, right? So it's not heating up anymore, which is not the ideal case. But for the more accurate temperature control, you do need a cooler and a heater at the same time. Do you have a cooler at home? For the thermostat, if you turn on the heater, it's a heater, right? You turn on the AC, it's the AC if you use in the summer. You cannot turn on both at the same time. So whenever the temperature hit that level, what's going to happen? I just shut it down and wait for a bit, right? And because this is just a 1-week tutorial, I don't want to make it super complicated for you guys. So what we are going to do is use a really simple light sensor. Okay, I'm going to come back here really quick. Let's look at the sensor we're going to use for this tutorial. So this is called a light resistor, light dependent resistor, LDR. Light dependent resistor, LDR. If it receives light, then depends on the brightness of the light, it's going to reduce the resistance, internal resistance to a certain level. If you got a stronger light, the resistance is just super low, down to like 20 ohms or something. But if you keep it dark, it can be 1 megohm, can be 10 megohm, 20 megohms, depends on the material and the pearl size of the sensor. So you can buy all different ranges of the dark resistance. I've used this a lot for one of the patent I just developed with a company, and so I just realized that they all have different internal resistance. But the cheap ones, usually the ones we have in the lab is usually like 500,000 ohms in dark, so it's pretty high. And if we make a circuit like this, 5 volts easily you can get from the Arduino, right, from the top, and you got LDR, and then the resistor, 2K to 10K. So 2K to 10K compared to, for example, 1 mega ohm is what? Like 2K ohms compared to 1 mega ohm is considered as what? No, considered as a short circuit. Considered as a wire. If you compare them, like, because you have these two resistors in series in this circuit, and this is super low resistance. So 99.99% of the voltage will be dropped across this LDR instead of here. You know what I mean? It's a voltage divider, right? You got two resistors sharing or dividing the entire 5 volts. I get a super high resistance in dark, for example, for the LDR. So the LDR is going to drop 99% of the voltage from the 5 volts. So if I ask you, if you keep the LDR in the dark, and what's the voltage across the two terminals of LDR? 5 volts. So which means this is considered, like I just told you, the 2K resistor, we'll compare it to a 1 mega ohm resistor, considered as a short circuit or a wire. Why? Because what's the voltage here? It's ground, right? It's 0 volts. Okay, you got 0 volts. What's the voltage here? I told you it's a short circuit. What's the voltage there? 0 volts. Make sense? That's why we consider that resistor as a short circuit. It's shorting that point to ground. Make sense? Okay. So if we keep this LDR in dark, the voltage at this point will be 0. Okay. If we turn on the light, keep it in the very bright environment, then the internal resistance of LDR becomes like 20 ohms. So 20 ohms compared to 2K is a really low resistance. Or we can consider the 20 ohms is a short circuit. So shorting this point to 5 volts. Make sense? Okay, so if you turn on the light source, what's the voltage here becomes after that? Still the same point. If you turn it on, if you turn on the light, the voltage becomes what? 5 volts. Make sense? Right? So we, in the first example, you have a little LED. You can grab LED from the drawers. LED can be any color, doesn't really matter. And have a 200 ohms to 1K ohms resistor as a current limiting resistor for the LED, so you're not frying that little LED. And you turn on the light, you can, see the differences of the analog reading from this point. So we have been talking about this point. Why not this point? Why we want to look at the voltage at this point, the changes at this point, not this point? As a power, that's always 5 volts. Okay, what about this point? It's always 0 volts. That's the point that varies. That's what we are looking at. Okay, and this voltage changes according to the light intensity. Make sense? So you're converting the light intensity into an analog voltage. Make sense? If you have higher voltages, brighter light, then lower resistance and higher voltage. Okay, if you have higher resistance, lower voltage. Why? Because higher resistance will drop most of the voltage from the 5 volts, so got nothing left. Okay, if you have some intermediate level of intensity of the light, then we got somewhere around like 2 to 3 volts. So you can get a continuous voltage change from like 0 to 5 at this point. Make sense? And then you connect this point to the A0 pin of the Arduino board, the Arduino Uno board, or you are using Nano, it's fine. So it's an analog input, it's a voltage input to the ADC, it's analog to digital converter on the Arduino. You don't have to know what's the circuit in there, but let's just use it. It's going to be an analog read function in Arduino. And you read it in and digitize it and find you can record it in your IDE and use it for other purposes. So you can show it in the monitor, and you can show a plotting, like the accelerometer's reading, like pulses, peaks, spikes. Okay, so you can do all these things. So for the first task, I think you want to know, because most of the time you set it up on the breadboard, you are working in one of the labs, but the light intensity in the different labs can be different. You know what I mean? So before you turn on that little LED, you put an LED pretty close, just next to that LDR. Before turning it on, you can measure the light intensity from the room. Okay, you just connect the circuit like this, and keep the LDR there. Don't do anything to it. And so the light intensity in the room can be read or can be converted as a voltage output, and then you can read it into Arduino. So for example, I just did this one. I'm just reading the A0 analog voltage, but didn't do anything else. See, just serial begin, then turns on the serial communication between the Arduino to the USB to the computer, and analog read, I read the analog voltage, okay, and then print it. It didn't do anything, but just reading the room light intensity. So you have a baseline. So you know, if you don't turn on the LED next to the LDR, you know what's the baseline of the light intensity in the room. And then you turn it on. Okay, in here, I have a pin 3, which is a digital pin on the Arduino. So I'm using that pin to turn on the LED. It's the output mode, so it's outputting voltages. And it's a digital pin, that's why it's outputting 1 and zeros, right? So if it's outputting a 5 volts or logic 1, it's going to turn on the LED. So I just keep it on, okay? And this is a PWM. You know PWM? Have you heard about that before? PWM? Yeah, some of you didn't have that experience, okay? If you have an LED, you can use 5 volts. Then there's an LED and resistor, right? Ground it. If you have a power supply, you can change the analog voltage output from 5 volts to like 3 volts. So you are getting you can dim that LED. If that makes sense. Okay, you can use a lower voltage to dim it. However, Arduino is not an analog power supply. It's a digital CPU. It's a system on chip. It's digital CPU. Okay, so it's not able to output an analog voltage. You know what I mean? You can input an analog voltage and use a little analog to digital converter, which is an ADC on the chip, to digitize it and convert it into binary numbers. However, the digital system cannot output analog voltages. So how do you use the digital pins, which only outputs 1 and zeros, to dim a LED? Seems like it's only 5 and 0 volts. It's either on or off, right? How do you dim it? That's a problem, right? So the engineers are pretty smart. They developed a new thing. It's a module in the chip. Okay, even though you can program in C language, you're programming in the C or C++ here, but it's actually being compiled and converted into machine code 1 and zeros, and as an instruction, and so the hardware actually using it is turn on and turn off certain functions in the hardware. in the chip. So there's a PWM module in there, okay, in the chip. It's a hardware, right? So if you do that, for example, if you program in this way, it's super convenient. You don't need to do anything else. Just like digital write, number 3, pin number 3, okay, and 255 is a number. You know, why 255? So what is 255? There's a lot of things that's not showing here, but you should understand what's going on. What is 255? 2 to the 8th, right? 2 to the 8th is 256. So why 255 is the maximum we can use? Because 2 to the 8th power is, you have 256 numbers, but I have to consider 0 as one of the numbers. So it's from 0 to 255. So we have 256 levels or numbers to cover that 2 to the 8th power range. All right. So these are all the options, all the numbers or intensity we have that I can put in there as intensity for the PWM. And why 8? Why 2 to the 8th? It's an 8-bit microcontroller, so which means all the registers in the controllers, there are 8-bit memory banks in the CPU. If you want to learn more about it, in the fall semester this year, take CE351, and you understand more about all these digital circuits in there. Okay, so 8-bit, and you already handle some of the 8-bit registers in the LCD sensors project. If you haven't, so it's still Friday. Okay, I just announced the new deadline for that project, for that tutorial. It's still Friday at 8 a.m. And if you go through that tutorial, you'll learn how to do interrupts and the timers, handle all the registers in there. You'll find out all the registers are 8-bit registers because it's an 8-bit computer system. But the laptops or desktops over there, these are 64-bit computer systems, which means the CPU takes out the instructions they are all in a 64-bit format, and then calculate to the computation and save it back to the memory also as a 64-bit data, right? That's a unit, the size of every unit memory bank in the CPU, in the computer system. But this is a very simple one, it's only 8-bit. So you set up the register, so the C++ program will be compiled by the IDE, and then being converted into the machine code. So the instruction here will eventually become binary numbers, actually, eventually being put into the registers. So that 255 becomes a 8-bit, which is 01s for 8 ones in a row, and being put into the register and being used as a intensity for or number or value for the PWM module. But how that works after that level, you don't have to worry about that, right? Because that's pretty down to the IC design. I mean, there might be a chance like we develop a new course project for Swiss RDA, like just develop a new PWM circuit. It's very possible, right? We can do it. And how the digital bits controls that PWM's duty cycle, which is a really fun project to work on. So highly recommend CE338 if you are not in the C program. In the C program, you have to take it anyway. Yeah, you'll like it, I think. And so that single line here is very simple, user-friendly, but however, it's being converted, it's going to be compiled into machine code eventually for the computer, but you're not seeing that. Just need to know they are all in batteries as an instruction in the future. Then what is a PWM? Let's come back to this topic. Since we have to use PWM because the digital system cannot output analog voltages. It only outputs 5 or 0 volts. It's digital oscillations. So if you want to dim that LED and it cannot output an analog 3 volts, so what you can do is you can change the duty cycle. So for example, this is 5 volts DC voltage. Okay, the duty cycle is pretty much 100%. There's no it's always on. It's not. There's no off, right? So what about also 5 volts but 50% duty cycle? 50% duty cycle. as just a standard square wave. It's gonna be like this. Okay, so 50% duty cycle means, so the duty cycle means the length, the time duration of the on period versus the entire period here. That's a duty cycle. Okay, so you can easily tell this standard square wave is a 50% duty cycle because it's just a 50% on and 50% off. Okay, it's a standard square wave. So this one, if you output the digital system can output oscillations, no problem. So you can write a on and off with a certain time delay with your Arduino board to oscillate it, to toggle it in a certain way. So you can change the time delay of for on or for off to change the duty cycle. So for example, you can make it like this, right? So that's why it's called pulse width modulation, or PWM. You can modulate the width of the pulses. Okay, if you have 5 volts, always 5 volts, you got 100% of the power. Okay, it's always 5 volts, it's a full power output. If you got 50% duty cycle, you're only outputting 50% of the power. Okay, if you have, for example, this is 10% duty cycle, you're only outputting like 10% of the power. So which means it's going to be dimmer. But why it's not blinking? LED is not blinking if you're turning on and off that pin. Right? So it's just too fast, right? So your eye cannot resolve it for most of the time. So that's how you dim it, how you dim an LED. Then, okay, so for the first example, what I did was I didn't do anything. It's just an analog read. I read that ambient light intensity, and I read it. I showed it in the monitor. And then the second example is I want to know if I fully turn on, it's 255. It's a maximum duty cycle I can give to the PWM, right? If you want to dim it, you can give 100 to it. So it's probably a little bit less than 50% duty cycle. It's going to dim the LED. You can try it, play with it. You can observe the changes. And is there any problem with it? Am I able to, if I just use this simple code, just read through it? It's very simple. I just added a PWM. So this one is going to turn on the LED, and then I immediately read the light intensity, and then I print it. So it makes sense, right? So the room ambient light, if I don't add anything to it, is 677, which is just a decimal number. There's no unit to it. If I turn on the little LED next to it, it's adding a lot of photons to that LDR. So it's increasing the voltage a little bit. Is there any issues with this method that I want to see what's the maximum light that the LDR can receive if I keep all the lights in the room on and also keep the little LED next to it on? I just want to know what's the maximum light intensity the LDR can receive. Is there any issue with this experiment based on the code provided here? For what? No. It's just making it more accurate. Yeah, that's right, but it's not changing too much. So what's the maximum value you expect? So the ADC we have on the Arduino is a 10-bit ADC. It's a 10-bit ADC. So which means the maximum value you can read is 1024, which is 10 to the 10th. Okay, 2 to the 10th power, which is 1024. Okay. So now if I don't do anything, I don't turn on the little LED on the board, I'm reading a 600 or something. It's probably somewhere around the halfway of the full range I can read, which is fine. Okay. Is it okay if I keep it in the darker room? You know, so I'm just reading like 300. Is it okay to do that? Yeah, it's even better. It's even better. Why not? So can I do this experiment in a super bright room and I'm just immediately reading a 1024 in there? What about that? Yeah, you can't change it anymore, right? You turn on the little LED next to it, it's not changing anything. It's already reading a max. Okay, keep in mind this is a PID control. We want to control it. We want to change it. Okay, so if I read a number like 600 something, it's somewhere around in the middle, which is fine, which is sounds like great. Okay, it's a good number to use. So if we are reading like 900 or 1020, what you want to do? Turn off the light. Okay. So after you turn on that little LED next to it, you want to see a change. If you're not seeing a change, something is wrong. Make sense? Okay, let's come back to this topic. Is there any issues with this code? Is there any issue with it? I turn on the LED and then I immediately read it. Am I reading more values? I keep reading it or I just end it? Is there a zero end? It's not reading a second value. So there's no chance to read a more accurate value. So why is this not accurate? Not really. Is Arduino running at which frequency? 16 megahertz is really fast. So and this is just the loop is only being executed once. So you power it on and it runs the program in probably less than 1 millisecond. All right. And you can see you turn on the LED here and immediately you read it. Do you think the LDR has enough time to respond to that LED's light? And you know there will be a time delay, but your microcontroller just runs so fast. You turn on the LED, read it, not giving a chance like to totally absorb that photon and make a change. Okay, so this number I'm reading here is actually lower or higher than the actual one, lower. You need more time to get more photon so you can get a higher value. So what you want to do here? What can you do to make it more accurate? You can read more values, right? But also you can do what? Where you want to add a time delay? Yeah, or right after you turn on the LED. Where did you turn on the LED? Digital write. Okay, so after the digital write, you turn on the LED, delay it for like a few seconds, and then read it. And you are reading 900. Okay, that's more accurate. So you know that if you turn on the LED, it's gonna reach like 900. All right. So what if you are still not reaching 900? You turn on the LED, it was 600, but you are getting like 650. What's happening? A few reasons, a few options. The LDR is fried. The LED is fried. It's not bright enough. And could you just put the LED closer to the LDR? Don't put the LED to the other side of the board, right? It's not going to receive any photon by the LDR. So just put it closer, just right next to it, okay? Okay, so for the PID, you have to learn how to tune it, right? So it has 3 different variables to adding the changes to it. So at the very beginning, this is original reading. The reading comes in, and that's the error. How do you calculate the error? By doing all these kind of things. So just need to follow, okay? So this is a proportional, integral, and derivative errors, and with a little gain in front of it. So is there a certain value or a certain way to find out the gain? No. You just have to try all the different values to make it work. So for example, why we don't want to just use the P gain or the PID that have 3 components, why just using P is not really making sense. Proportional means it's just linear change. Why is a linear change? Because you can see this is error, right? ET is an error, which is a function of t, because you are running the system along the t domain, in the timing domain. And whenever you get a new error and times a constant, which is it's called a P gain, proportional gain, and just a constant you put in the program. Okay, so the error times the gain and becomes a final result, final error being fed back to the input, right? And then being added to the original input, and then being sent into the system again, and then calculate the next error. So what's happening here actually? We are not considering the integral and the derivative yet, right? Just the proportional. How that works. So we have a setup value, right? So for example, the intensity at our beginning, that's 677. That's the light intensity from the rule. I just read it from the Arduino. That's the very beginning intensity level. It's 677, right? And this is a maximum 923. Very quick quiz question. I think you guys already got it, but let me just ask. How did you get this value? Where did you get that value? Ambient light. So if today you come to the 602 lab and tomorrow you work in the 570 lab, you have to adjust that value? Yes, it's going to be different. Next time you bring it home, it's going to be a totally different intensity, all right? So where did you get this value? Yeah, the ambient light and also plus the LED light. So that's the maximum light you can have, right? So in that case, you know that's the minimum and max, right? Could you dim it? Could you dim it below 677? In the control system, could you dim it in the real-time control when you're controlling it, right? Can you dim it? Yes. Why? I mean, in the control system, that's you. You just said, right? You said you can. That's you. You are not part of the Arduino board. We are going to automate everything, but you are not part of the Arduino, right? You cannot just wire you up, solder your fingers to Arduino, and do a real-time control. You sense that 5 volts, then your finger just keep turning on. You just couldn't do it. Make sense? You are not part of the control system, so you cannot do it. So can you dim it? In the control system, can you dim it? Based on the circuit I provided in the tutorial. No. If you are creative, you can let me know how you can dim it later, but you cannot dim it because the light sources from the lights from the ceiling. How do you interface these lights with your Arduino system? There's no way to do it. So cannot dim it. Makes sense, right? So so for the control system, I want to set up, it's called a set point. Make sure you understand what I'm talking about right now. It's like a thermostat at home. You want to set it to 67 degree, right? It's heating up. Sometimes it's going to overshoot to 68, and then it's going to shut down the system and wait until it reaches a set point. So we have a set point. This is what we need, all right? This is what we need. So Should we make the set point in the middle of these two values, or can we set the set point somewhere else? Based on the circuit we have, can we set the set point at 924? Can your control system reach that point? How? But I already told you that's the maximum photon or intensity I can provide to the system. You can add another LED next to it, right? You can add a second one if you like, so you can change the maximum to like 1000. But in that case, could you, if you only can do one LED, you only have, that's everything you have, can you set the set point at 924? No, there's no way, right? Sorry. Okay. Can you set the set point at 676? You cannot dim it. Okay, so it has to be in the middle. So the best way is find out the value in the right middle of the between the two values, right? You have to calculate it every time based on the environment intensity, and then you find out the middle value at the set point, right? So the control system can make it happen just by itself. So your finger is not part of the work, part of the job, right? So turn it on, the PWM is going to do the job for you, right? So if we only use proportional PID, only use the P gain, we turn on the system, then it starts from here. It starts from here. All right. Makes sense? Because at the very beginning, I don't want to turn on the LED because the room light is this, and then it's going to calculate the error. So in your C++ program, you just make a subtraction. It's very simple subtraction. It can find out the error, which is this gap, right? So the middle is a set point. That's a goal. But at the very beginning, the room light cannot reach it, so there's an error. So at this time point, you got an error, which is ET0. At that time point, T0, the error is E. Okay, we're only using the proportional gain right now, for example. Okay, then what's going to happen is it's going to times the gain to it. Why do we have to times the gain? Because they're a different system. What's the problem here? They may have a different unit, you know. You are reading a intensity, and but you are feeding a PWM. They're not the same thing, right? Are they the same thing? No, you are reading intensity, which is like 700, but can you actually feed that 700 to as a PWM? Can you? Hey guys, can we, for example, so the error here right now, for example, the first point, right? If we set this one at 800, for example, let's just assume so 800 as a set point. It's just a simple subtraction, so the first error becomes 123. 123. That's the error of the light intensity. That's a binary. So it's in the ADC's value. It's a subtraction of the binary readings, right? It's not necessary to be the PWM that you want to use. So to modify this output, you have to modify this error. So the gain doesn't have to be like larger than 1. Sometimes it's just a fractional value like 0.3, 0.5, 0.0001. Doesn't matter because they are totally a different number scale in a different system. This is a binary number from the ADC, but you need another number within the 0 to 255 range for the PWM, right? So I have to times the gain, so the gain will rescale it to the range that we can use for the PWM. That's why you have to use the gain. Make sense? And you times again, for example, it's going to change the value proportionally, which will be a DC, will be a linear change because this is directly just a constant times the error. So it's a linear change. It's going to be a linear change. So it's going to, for example, it's going to move this one like this much. Okay, it's going to move it like this much. It's happening really quickly. We're just slowing down everything frame by frame, time point by time point. But actually, every loop, it runs like within 0.1 milliseconds, right? Really fast. So next time, the intensity becomes here, and you got a new error. All right. After the new error, it's a linear change, which means it's adding a constant value next to it, right? And then you got a new error here, right? But it's just, ignoring that, not ignoring, but, it's just not that smart. Just keep adding a constant value to it. Okay, that's the final result, which is the intensity becomes here. So the PID system or the P system will find out, oh, I'm overshooting. Okay, so it's gonna starting from here and move it back. Oh, I'm lower than that, so let's add it to it. Next, overshooting again, come back. So what's happening here? It's oscillating and not giving you an accurate result. So we want to just use a linear control system. That won't work. It's going to do some kind of job, but won't work accurately for the system, right? So it's going to oscillate. It's a constant. Okay, so that's why you need the nonlinear components. A lot of times, it's not always necessary to have all PIDs. So these are just trying to smooth the when it's approaching. So for example, when it's getting here, right? Instead of overshooting like that, it's gonna try to approach it like this. Maybe a little bit overshoot, but will come back smoothly, instead of linear as a P controller. But a lot of times, if you just use a P and plus a like I controller, like PI controller or PD controller, it's gonna do the job. It's always good enough. But sometimes you probably want to use all of them. But based on the undergraduate level class, we don't have to dig too deep into the details and find out the errors. Optimize everything. It's just not that important. Okay, I think for this tutorial we probably only used P or only P and one of the IRDs. But the programming is pretty simple, and you can find out how to implement a integral or how to implement a differential or derivative in the C++ really easily. It's everywhere. Examples everywhere. Just Google, it's everywhere. But I provided several examples to show you how do you implement that kind of equation. So for integral, it's just every loop after every loop. You keep adding the new values to the old values. That's it. But for derivative, you just subtract the errors from the previous value. It's pretty simple. So what we are going to do here is, after you know the circuit system we are going to build on the board, so let's see what's going to happen. So for example, if we don't have a second LED, it's only one LED, like this one, can we make a PID controller or not? So there's no fingers involved, right? So this is shorted to the PWM pin on Arduino. If we set a setup point, like what I just showed you here, in the middle, and then I turn on that system with this circuit on the breadboard, can I have a little controller that will maintain the reading to be 800 instead of something else? Is this going to work? Yeah, it's going to work. right? Because the Arduino is going to read the value at the very beginning, it was 600 something, and then the PWM is going to output a certain value to not fully turn on the LED, but just turn it on to a certain value using the PWM signal to keep its sensor reading at somewhere around 800. It's going to work. Make sense? Okay, that's the first task we're going to work on. And second, if you add another one, so what I want you guys to do here, if you add another one, okay. So look at this pin here. There's no PWM, it's directly 5 volts. Okay, so you already built everything here. It's a little controller, and you can tell that the PWM is controlling the intensity of this light in real time. And sometimes you couldn't visualize the changes because it definitely won't be a constant intensity. So if you put for example, you put a paper in between the sensor and the LED, what's going to happen to this LED? No. Let's come back to this circuit. So for example, you build this circuit on the breadboard, okay? And then the PWM is not fully turned on because you want to maintain 800. If you put a paper in the middle of the tool, you block the light from the LED to the LDR, what's going to happen to the LED? It's going to turn it fully on, right? But still not reaching 800 because you block all the light. But the LED has been trying very hard to try to make 800, but it just cannot. So you'll see the difference. So it's a very similar interference, okay? So I'm gonna have so if you block whatever on the top, right, just look at this one, there's no difference, it's the same circuit. And then you just add another LED on the top, but you have a little push button, right, it's a push button to turn it on off, and which is 5 volts, not PWM anymore, you just want to turn on off something to interfere with your control system, see if it works, right? Okay. Now, if I push this push button to turn on the second LED, what's going to happen to this LED? Why? Yeah. So the PWM is something you can control. The microcontroller can control. So that one is being controlled to get dimmer in order to make the overall reading to be what? Yeah, 800, the set point. So see the changes, all right? And I have then the very last one, which has a little debounce circuit here. Make sure you understand how to debounce it, because when you push the push button, it has a lot of bounces. The mechanical system, the push button, when you push it, it's not directly giving you a clear 1 and 0. You should know that. It's a very important concept. It's actually bounce back and forth because the mechanical system, you couldn't feel it, you couldn't see it, but actually the little metal, the spring or the contact is bouncing back and forth. So you need the software to debounce it. Okay, try to understand what's going on for this little debouncing code. It's going to show up in one of the exams later on or quizzes. And what we're doing here is we push the push button to change the set point, and your PID controller can follow a new set point. That's the very last task. It's a little bit more advanced. But when you push the push button, you'll see the blue line is a new set point, and the reading is going to track that set point after you push it. Every time. So you can change the set point in real time, and the PID controller will be able to track it. Make sense? That's the easiest way to learn PID control by far, as I know. It's just the 2 resistors. That's the best way to learn it. You don't want to mess with all the heaters and coolers and motors. going to spend the whole semester to learn PID control. So that's the best way to learn it. So make sure to explore all the details. And there are some, there's a typo in one of the code. It doesn't really matter because I didn't use it anyway. Which one? I controller, I guess. Oh, this. Sorry, give me a second. This one. So I have a note here, right? There's a typo for this code, but it doesn't matter because, so for C++, you should have I plus equal, right? It's a little syntax error, but I didn't use I, so that's why it doesn't matter because the I gain was 0, right? So, or eventually it's still 0. It doesn't matter at all. Just let you know there's a typo there, okay? And LDRs, you should have LDRs in the box. If you don't have it, I will grab one for. Let me grab one. These are LDRs. The one. I got it. Yeah.